And now we want to go and look at the fourth part of our lecture. Now, as I mentioned before, Galileo is someone who did a lot of experiments about motion. And from those experiments, he was able to really understand how motion works. And he's the one that came up with the concept of acceleration. Now, for us today in the modern world, it doesn't seem like that big of a deal. I mean, you have a car with an accelerator pedal. We kind of understand what acceleration is, but back in Galileo's day, people didn't really understand the difference between acceleration and velocity. And even today, sometimes my students will mix it up in certain situations where it's a little bit confusing. So we want to be clear about what acceleration is, because this was an idea that Galileo put forward through his experiments. And specifically, he studied the motion of balls as they rolled down inclined planes. And what he noticed, remember I talked about how he had that bag of water dripping as his clock. So drip, drip, drip. Every drip, he would mark on his plane the position of the ball, and he could see that as time went on, the ball was traveling bigger and bigger distances. In other words, in this tick of the clock, the ball traveled this far. In the previous tick of the clock, the ball only traveled that far. Clearly, that distance is less than that distance. So each tick of the clock, the ball was going faster and faster. It was covering a bigger distance. And so what Galileo recognized was that not only was the position of the ball changing down the inclined plane, but also its velocity was changing. It was going faster and faster. And so we can define a concept that tells us how the velocity is changing, and we call that acceleration. And so here again is our definition. The definition of acceleration is the change in velocity over the time. So change in velocity over the change in time, or the time interval. So let's apply this to an example. Here's our example. An object is moving 10 meters per second, and it increases its speed to 20 meters per second, and it takes 2 seconds for that to happen. The question is, what is the acceleration of that object? And so we can look again at our definition. We say it's the change in velocity over the change in time. But what does that mean, change in velocity? That means the final velocity minus the initial velocity. This guy right here, v sub f, that's what we're calling the final velocity. And this guy right here we could call the initial velocity. So final minus initial, that's what change is. And so now we can simply plug in the numbers. The final velocity was given in the problem to be 20 meters per second. We subtract from that the initial velocity, which was 10 meters per second. 20 minus 10 gives us 2. Now for our time interval, we have it took 2 seconds minus 0 seconds. That's our change in time. And that gives us 2 seconds as our time interval. And so if we divide 10 divided by 2, we get 5.0 meters per second divided by seconds. That means every tick of the clock, the velocity increases by 5 meters per second. It changes 5 meters per second every second. Now, we don't normally write the units this way, but that's what it means. It's how much the velocity is changing every second that ticks by. Now, mathematically, both of these s's are being in the denominator of this fraction. And so if you multiply two s's together, you get s squared. And so the normal way that we would write the acceleration with proper units is we would say that the acceleration is 5.0 meters per second squared. And so mathematically that's how you do it, but what it means is 5 meters per second change every second. In other words, in the first second, it increased from 10 meters per second to 15 meters per second. In the second, it increased from 15 to 20. Every second is an increase of 5 meters per second of velocity. So here is one of these check our understanding things from our textbook. And so let's look at it. It says, in 2 seconds, a car increases from 60 kilometers per hour to 65 kilometers per hour, while a bicycle goes from rest, that means it's 0 kilometers per hour, to 5 kilometers per hour. Which one has the greater acceleration? Pause the video and write down what you think the answer is. Really do it. Just pause the video. I'll wait. Write down what you think the answer is, and then come back to the video and we'll check your answer. I know you don't want to do it. Will you really do it for me? Just pause the video and try to figure it out. Let's see if you can understand what we're doing. Okay? I'll wait for you. All right. I hope you did it. Let's look at it now. What's the definition of acceleration? We can say that acceleration means it's the change in velocity over the change in time. And you can see I've written this fancy looking triangle here. That's actually not a triangle. That's the Greek capital letter delta. And in science, delta often is a substitute for the word change in. It's just sort of a shorthand. And so I would read this as the acceleration is equal to the change in velocity over the change in time. So what's the change in velocity for each case? Going from 60 to 65, the change is 5 kilometers per hour. In going from rest, or from 0 to 5, again, the change is 5 kilometers per hour. And in both cases, the change takes 2 seconds. So the change in velocity over the change in time is the same for both cases. Neither has the greater acceleration. They both have the same acceleration. And that's what we end up with. A is the same for both cases. The acceleration is the same. The next thing we want to look at is the fact that, like velocity and like displacement, acceleration is a vector quantity. Its direction matters. And so we want to look at how the direction of acceleration can affect motion. Now, I've drawn in my picture a little XY coordinate system to define which way we're talking about. And so I could have just said we're going to the right, but we're going to be really specific and say we're going in the X direction here. We're going along the X axis of my coordinate system, and both my velocity and my acceleration vectors are pointing in the positive X direction, or to the right. Remember, we said to the right is positive. It's really what we mean is we say that's usually how we draw the X direction, and both of these are in the positive X direction. When that is the case, when both the velocity and acceleration are in the positive direction, the speed of the object will increase. It'll speed up. Now, don't read the stuff on the right yet. Let's just look at the picture to start with. What's different about this picture? The A is pointing in the negative X direction. The acceleration is in the negative direction. Now, it turns out that in this particular case, the object is going to slow down. But this is a little bit misleading. So what happens is people see this picture and they think that a negative acceleration means that the object is slowing down. That's not the case. It's true in this specific example that the acceleration is negative and the object is slowing down, but it's not because the acceleration is negative. Why not? Well, let's look at a third possibility. What is the situation here? V is in the negative and A is in the negative. They're both in the negative. What do you think is going to happen here? What's going to happen is they're going to speed up in the negative direction. And so here's a case where A is negative, but the object is not slowing down. In the previous slide, the object was slowing down, but not in this slide. What's the distinction? Basically, it's this. When the velocity and the acceleration are parallel, that means they're in the same direction, the object speeds up. But when the acceleration is in the opposite direction from the velocity, the object slows down. So the negative just means whether it's going to the left or the right. It doesn't mean speed up or slow down. What tells you whether it's speeding up or slowing down is if they're in the same direction or in different directions. Let's see how this can work in the real world. Imagine you throw a ball into a really strong wind. So you throw the ball to the right, it's got a positive velocity, but the wind is slowing it down. So we know the acceleration is in the opposite direction to the velocity. And so the ball is going to slow down. Eventually, just for an instant, the ball is going to stop. It has to stop in order to turn around. And so for just a moment, the ball is going to stop moving, but the wind is still accelerating it to the left. So it's going to start speeding up to the left. And over here, what's going to happen is it's going to continue to speed up, and so the velocity is just going to get bigger and bigger in the negative direction. And that's all there is to it.